Okay, welcome everyone to the last day of what's been a really incredible workshop. The first talk today by Mrinal Kumar of TIFR will be telling us about exciting recent developments in polynomial factorization algorithms.
Thanks, Bill. I'm audible. Thanks for being here, and thanks to the organizers for inviting me. So this talk is supposed to be sort of a survey, but I'll also talk about some recent work, and I do intend to talk about some proofs through the talk. So yeah, if you have any questions, please stop me and ask. Most of this work is based on joint works with Somnath and Shubhangi from Toronto, Ramprasad, Shanthanu, and the recently anointed Dr. Ramanathan from TFR. Okay, great. So this is not a great way to start a talk, but I promise this is the only such. So let's fix this notation for the entire discussion. N will be the number of variables, D will be the total degree of the polynomials we are interested in, S will be the circuit size, and both S and D are going to be poly n throughout. And the underlying field, most of what I say will hold over other fields also, but the fields to have in mind should be rational numbers or complex numbers. Okay. Great, so here's the primary question we are going to be interested in. We would like to design an algorithm that the input to the algorithm is an n-variate polynomial f of degree d, and the polynomial is given to us as a small circuit, and our goal is to output the factorization of f into as a product of irreducible factors. And as the problem says, we are going to the output is also going to be, the intended output model is also going to be circuits. So we would like the algorithm to output circuits for the factors of f and tell us what the multiplicities are. And before we go further, at this point, if you haven't seen this before, you should ask, is this even a reasonable question to ask? Can we expect efficient algorithms for this problem as stated here? And the reason for that is that it's conceivable that the factors of f do not have circuits that are polynomially bounded in the circuit size of f. And this is not a completely rhetorical issue. This is not true for sparsity, which is sort of the most natural initial model that one would think of representing polynomials. So for instance, consider this polynomial f of xy, and the number of monomials that this polynomial has is about 2 to the n, maybe 2 times 2 to the n. But here's a factor. So g of xy is an irreducible factor of f of xy, but the number of monomials here is more like n to the n. So the sparsity of f is exponential in n, but the sparsity of g, which is a factor of f, is exponential in n log n. So there's a quasi-polynomial growth in the sparsity in the process. So this question of whether the factors themselves are computable by small circuits it's an important and extremely non-trivial part of this problem as stated here. Okay, great. So everybody agrees that this is a natural algebraic question about polynomials. And unlike many other natural questions in computer science, this one has a solution from the 80s. So a long line of work, sort of culminating in a work of Kaltofen in the mid-80s, proves the following theorems. So it shows, first of all, that factors of polynomials with small algebraic circuits have small algebraic circuits. I'll just point out here that we are under the assumption that the degree of the polynomials is polynomially bounded in the number of variables. This was an issue that also came up during Anakin's talk yesterday. Okay, so we are in that setup. So, and in that setup, Kaltofen showed that if you have a polynomial f which has a circuit of size s, then all its factors are circuits of size poly in s and the degree of f, which is poly in s in the setup we are in. So this was one part, and this closure result, this says that algebraic circuits, at least in the low degree regime, are closed undertaking factors. This this already tells us that the question we asked about designing efficient algorithms for factorization is a reasonable one to ask. The output description is polynomially bounded in the input description. But it didn't stop there. Kaltofen also gave an efficient randomized algorithm that will take an algebraic circuit as input and output its factorization. So output circuits for all the irreducible factors and tell us what their multiplicities are. Right, so this very, very convincingly answers the question that was there on the first slide. I think it doesn't happen very often. The result was extended to the black box setting by Kaltofen and Traeger about 5 years after this work. So in the setup there is that our input is a black box access to a circuit for a multivariate polynomial, and the output will also simulate black box access to the factors of the polynomial in the process. So very impressive. You don't even have to look inside the circuit in order to factorize. I think it's an extremely fundamental result. I also think it's one of these very it's not a known enough result even within the complexity audience. We know it in an algebraic complexity audience, but generally not known and not appreciated as much as I think it should be. It's extremely surprising because the closure result, to me, I don't know if there was a reason a priori to expect such a closure statement to be true. The long line of work that happened that led to the theorem introduced a bunch of new techniques that continue to find users within complexity in algorithm design, in coding theory. And there are some amazing consequences to classical complexity theoretic questions like hardness randomness trade-offs. So all in all, a very important theorem. If there's nothing else to take from the talk, this theorem is something that's worth knowing. And because it's a very important theorem, people have looked at it over the last 3 decades from various new perspectives, and there are various known proofs at this point. The earliest proof that I know of, the proofs that I read the first time were actually lecture notes from a course that Madhu taught in '98. But the exposition that I like the most now, as of today, is from a paper of Peter from the late '90s. Okay, great. So then Kaltofen, so we had a very nice question. Kaltofen came and solved it, and this was in the 80s, so we are all done. But there are a few things left to be done. And there are, so I'll point out 4 questions that I think are sort of open and then new things to understand here. So the first question is that of de-randomization. Kaltofen designed an efficient randomized algorithm for polynomial factorization. Can we design efficient deterministic algorithms for polynomial factorization? So that's one question. Now this question is sort of generally tricky. Intuitively, factorization should feel like a harder problem than doing polynomial identity testing, and you can make it formal. So we know that this is at least as hard as deterministic PIT for circuits. So first step towards saying something interesting here could be to deterministically factor polynomials which have some additional structure. So for instance, they are computable by constant depth circuits, or they are sparse polynomials. So this additional structure ensures that we have non-trivial PIT algorithms for them. So maybe we can ask for polynomial factorization. Yeah, and the example that I suggest you should keep in mind is that of sparse polynomials. We are given a polynomial with which only has poly and monomials. We want to factor it, and we have known deterministic PIT for sparse polynomials from the early 90s. So we understand that problem very well. So can we factor? The second question, second family of questions of interest here are to understand if other natural classes of polynomials are closed under factorization. So suppose that the circuit for a polynomial has additional structure, like it has small depth, or it's a formula, or it's sparse. Do the factors of the polynomial, or do the irreducible factors of the polynomial also inherit these properties? So that's a natural question. The third question is to understand the question of closure under factorization over fields of small characteristic. And so I'll not state precisely what Kaltofen proved here, but here's a problem that is open, and this will address the issue. And the question is, suppose we are over a field of characteristic P, so let's assume 2. So we are over a field of characteristic 2, and we have a small circuit that computes the square of a polynomial. Does the polynomial have a small circuit? Right? It almost feels like the answer should be yes, right? But we don't know how to prove this. The best bounds we know are incur p to the n blow up in size in the process. So if f to the p has a circuit of size s, then we know that f has a circuit of size p to the n times s. This is the result of Robert from a few years back. The fourth question is that a factor conjecture, which also came up yesterday in Anakin's talk. And so here the setup is that suppose G is a polynomial that is of degree poly n, and it's a factor of a circuit of size poly n, but the degree of the circuit, the polynomial computed by the circuit, is exponentially large in n. And we would like to understand if G has a circuit of size poly n. Kaltofen's result as it is only tells us an exponential bound on the circuit complexity of G. We would like to know if that bound can be improved to polynomials. We know because of a result of Peter that G is in the border of circuits of size poly n, but we don't know how to prove a statement that does not involve it. Right, so these are sort of four questions that I think are very natural questions that have been open for a while. This talk we will focus on the first two questions. So we'll talk about closure results for other natural classes of polynomials, and we will talk about the question of designing deterministic algorithms for polynomial factorization when the polynomial itself is let's say a sparse polynomial or has a small constant of set. So these are the two things that I want to focus on. So through the talk I hope to get through some of the technical ideas in the proof. Some high level technical ideas are quite nice and I think easy to communicate and understand. There are some technical details which we will sort of gloss over. But because I want to do talk about some of the proofs, we will miss some of the important results on the way. So in that sense, this is not a great survey of what is known about polynomial factorization. Great. So let's first talk about the question of closure under factorization, and then we'll get to the question of de-randomizing deterministic algorithms for polynomial factorization. So amongst the closure results, we know that algebraic circuits are closed under taking factors. So complexity theoretically, what this means is that the complexity class VP is closed under taking factors. This is from Kaltofen's result and Peter's proof later. The other set of closure results were so there were results proved by Dwyer, Amir and Raphael that showed that formulas and constant depth circuits with bounded individual degree are closed under taking factors. Pranjal, Saxena and Sinababu, and in a joint work with Chining Chow and Solomon, we showed that the complexity class VNP is closed under taking factors. Amit and Thomas showed that algebraic branching programs are closed under taking factors just a few years ago, about 5 years back. So the class VVP is closed under taking factors. So these are all very clean closure results. And here's a not so clean closure result. This showed that low degree factors of constant depth circuits have small constant depth circuits. What's low degree? Well, think of degree being sublogarithmic in n. Growing but sublogarithmic in n. The reason I'm mentioning this here is because this result, it's a weird statement to have, but this found some use when combined with the lower bounds for constant depth circuits of Nutan, Shrikant and Sebastian. This gave deterministic PIT algorithms for constant depth circuits. And that's something that will come up later. Okay, so these are some of the highlights of closure results that we know since over the last many years. And so here's a theorem I want to state. So this is going to talk about closure of constant depth circuits under factorization. So in a joint work with Somnath, Shanthanu, Varun, Ramprasad and Shubhangi, we showed that if a polynomial has size S circuit of depth K, then its factors have circuits of size poly S and depth K plus 10. And that 10 is, 10 is something. It could be a smaller value of 10, a larger value of 10. Okay, so this shows that constant depth circuits are also closed under taking factors, except the depth increases additively by a constant in the process, and the size only blows up polynomially. Are we good with the statement?
You don't say anything about the degrees here?
So degree is everything is polynomial. Other questions? Okay. So the proof turns out to be relatively simple and fairly modular, and we will talk about some aspects of this proof later in the talk. there are two main ingredients in this proof. One is an amazing result of Furstenberg from the 1960s, and the second main ingredient is sheer blind luck to stumble across this result and realize that it's useful. So one of the aspects of this proof is that this essentially recovers all the closure results that we saw in the previous slides and some more stuff. And it turns out it has some interesting applications. One of them is to harness randomized trade-offs for constant depth circuits. And then Shantanu in the next talk is going to talk about some more applications to GCD computation for constant depth circuits. Okay. And the plan is to discuss some of the main ideas in the proof. Great. Questions? Okay, so this is one of the theorems that we are going to dwell a little bit more on later in the talk. Great. Okay, so now let's get back to the second question, which was of deterministic factorization. Amir and Ilya noticed some time back that the question of de-randomizing factorization, or even the question of testing if a given polynomial is irreducible, it's at least as hard as PIT, deterministic PIT, for the class of circuits that we are working with. Okay, before we go ahead and try to de-randomize PIT, we better have a de-randomized factorization. We better have a deterministic PIT algorithm for the class of circuits that we are working with. And Shubhangi, Swastik, and Amir later showed that there's a connection in the other direction as well, at least for general circuits, in the sense that if we had deterministic PIT algorithms for general arithmetic circuits, then this would give us deterministic polynomial factorization. This will de-randomize Kaltofen's algorithms for factorization. The issue with the second result is that it doesn't scale down. This is a statement about circuits, about general unbounded depth circuits. It says that if you have deterministic PIT for general unbounded depth circuits, then you get deterministic factorization for such circuits. If you want to invoke it for, let's say, constant depth circuits, you still need deterministic factorization for deterministic PIT for general circuits. So it does not scale down. So one of the questions to ask is to understand if deterministic PIT for constant depth circuits suffices for deterministic factorization for constant depth circuits. So does this statement actually scale down? And for starters, the potentially simpler question is to design a deterministic algorithm for testing the irreducibility of sparse multivariate problems. Alright, so now let me mention a result. So maybe a couple of years back, we showed that there is a deterministic sub-exponential time algorithm for factorization of constant depth circuits. Okay. Questions? Okay. So in particular, we can test the irreducibility of sparse polynomials in deterministic sub-exponential time. Okay. Great. So strangely, the deterministic algorithm actually predates the closure results for constant depth circuits. So at the time of this proof, we did not know if constant depth circuits were closed under taking factors. So this algorithm, it takes as input a constant depth circuit, but the output circuits for the factors is of unbounded depth. At least was. And then we later realized that this proof can be substantially simplified by using the closure result, and we can ensure that the factors, the output circuits, are also constant. Okay, so originally these were unbounded circuits. Great. Questions? So these are the two results we are going to talk a little more about. We will talk about the question of closure of constant depth circuits under factorization, and we will and for the deterministic algorithm part, I'll focus on the question of testing irreducibility of sparse polynomials.
Maybe one question, because you say in particular, is it clear if you have what you say stated the first line
Right.
for constant depth, then you have irreducibility testing for sparse?
No, it's not clear. It's not.
In fact, it's not clear.
No, it's not. It wasn't clear at this time because the output circuits were all unbounded depth. We didn't know how to do PIT and do divisibility testing. but combined with the closure result, it is clear. Other questions? Okay. So now is a good time to start to ask questions. If something was unclear, we'll move on to the proofs. And okay, great. So let's move on. So let's talk about some high-level ideas in the proofs, and some of the ideas at a high level are quite nice. So let's start with the proof of the closure result. So the statement was, if a polynomial has a size circuit of depth k, then its factors have circuits of size poly x and depth k plus a constant. The proof of this the proof is in three main phases. Roughly in the first phase, we'll do some pre-processing on the input. We'll make it look nice, have some nice properties, without destroying the circuit structure too much. In the second part of the proof, we will talk about the roots of these polynomials. I'll elaborate on what that means. And most of the new ideas in our proof are actually in this phase. And then we will go from the complexity of our understanding. We'll use the understanding of the complexity of the proof of the roots to conclude our theorem, which will tell us something about the complexity of arbitrary factors of this polynomial. Okay, so let's start with pre-processing. So here's how we should think of the input. Let's think of the input as just being a sparse polynomial. Let's not worry about it. This is a very special case of conjugate circuits. And we would like to show that all the irreducible factors of f have poly size circuits of depth order 1. So with a little bit of work, we can ensure that f has some additional structure that helps us proceed with the later steps better. The first thing we would like to ensure is that f is monic in Y. So there are two sets of variables here. So there's boldface x, which is, imagine that being an n-1 tuple of variables or an n tuple of variables. And there is a special variable y. We have a specially labeled variable y. And we would like to do something to f to make sure that it's a monic polynomial in Y. The second thing we would like to ensure is that f is square free, meaning it's not divisible by the square of a polynomial. And the third thing we would like to ensure is that f remains square free even when the x variables are set to 0. Even when we set all the x variables to 0, so at that point f becomes a polynomial f of 0 comma y. It's a univariate polynomial now in Y. And we would like this univariate polynomial to be square free. It shouldn't be divisible by a square of a polynomial. In particular, it shouldn't have roots with high multiplicity. Multiplicity more than 1. Okay, so these are the three things we would like to do. And if f happens to be a square free polynomial to start with, the first and the third things, ensuring that f is monic in Y and ensuring that f remains square free even when the x variables are set to 0, can just be done by basically translating the x variables in the following form. So we replace the variable xi by xi plus ai times y plus bi, and we can pick ai's and bi's at random.
Now you're losing sparsity?
Now we will lose sparsity, yeah. But it will still be the depth doesn't increase very much. So okay, so if we start with a square free f, this translation will help us ensure the other two properties. And when we talk about the deterministic algorithm, we can't shift by a random a1 up to an, b1 up to bn. So there we will have to be a little bit careful, but we'll worry about that when we get there. Okay, so going forward, let's assume that we are given a square free f, and we do this sort of a change of basis which ensures that f becomes monic in Y and it remains square free even when the x variables are set to 0. Great. So now we will assume that f has all these structures. So this will make our lives easier going forward. Now, f of 0y is a square free polynomial. It's a square free univariate. So let a1 up to ad be the roots of this univariate polynomial. The roots live in complex numbers, for instance. And by the way, because f of 0y is square free, each of these roots are distinct. They are all ai is not equal to aj for I not equal to j. So what we are going to do now is to view f of xy as a univariate in Y. So we are going to think of this multivariate polynomial as a univariate in the special variable y, and the coefficients of this univariate polynomial are polynomials in the variable, in the x variables. So the coefficients are in the ring C adjoint x. And this ring C adjoint x, this is a ring of polynomials with complex coefficients. It's a subset of the ring of power series in x. So the difference between, if you haven't seen this before, the difference between a polynomial and a power series is that a power series has infinitely many terms. It goes on forever. So C adjoint x is a subset of the ring of power series in x. So we can view f as a univariate in y, where the coefficients live in the ring of power series in x. Okay. Now we are going to try and compute the roots of this univariate polynomial. So this univariate polynomial in y with this the roots live in some complicated ring, and we are going to try and compute the roots. So the first question would be, oh, what do the roots even look like? And because of all the setup we have done, there is a nice answer to what the roots look like. And the root, so the claim is that the roots, the y roots of f, they also live in the ring of power series in x. After all the pre-processing, this is what we get. So the roots of the y roots of f live in the ring of power series in x, and the coefficients are complex numbers. Alright, questions? Okay. Furthermore, for every a, so for every root of f of 0 comma y, there is a unique power series phi of x, such that f of x comma phi of x is 0 and phi of 0 is a. So let's parse this slightly differently. So when we set the x variables to 0, we got the polynomial f of 0 y, we computed it, we picked one of its roots, let's say a. This theorem says that for every such a, there is a unique power series root that lifts from this a. Questions? This is a yeah. I mean, if you have seen some version of this at some point, this is a formal
Phi
statement.
of 0 the same as phi of x mod x?
Right.
Or
Yes, it's the same as phi of x.
it's not like an evaluation.
No, yeah, but since it's in power series ring, we are allowed to set x to 0. This evaluation is legitimate. Great. So we'll have to look at other aspects of this theorem, but are we good so far? Is the statement clear? Okay. So this theorem in this form is not going to be enough for us. What will be important for us is this process of computing phi of x from given this a. So this theorem tells us that there is a unique phi of x given this a. But it will be important for us what phi of x looks like. So in fact, the theorem tells us more. It tells us that we can actually iteratively construct phi of x starting from a, one homogeneous component at a time. So phi of x is a power series. It contains monomials of degree 1, 2, 3, 4, blah blah blah. And we are going to construct phi of x with by constructing one homogeneous component of it in every iteration. Okay, so let's define phi sub I to be phi of x mod x to the I plus 1. This just means this is the part of phi where we have thrown away all monomials of degree more than I plus 1. So we just retain the monomials of degree at most I in phi. That's phi sub I. And then we just set phi naught to be a. This was the guarantee of the theorem. And the way to construct phi x, so and now we have a way of constructing phi I from phi I minus 1. And inductively we set phi I to be phi I minus 1 minus f of x comma phi I minus 1 over beta. What's beta? Well, beta is the y derivative of f evaluated at 0 comma a. Okay, so let's just stare at the form of phi I. So phi I takes phi I minus 1 and then plugs it into f and gets something and scales and adds. That's what's happening. Why is beta non-zero? We know that beta is non-zero. Why is it non-zero? Right, because f was square free and a was a single root. So beta is non-zero. Great. There are other versions of this inductive process which are far more efficient, but this is what we are going to work with. It's simple and clean to think about. Okay, great. So this is the definition. So starting from a, this is how we define phi, and then one can go ahead and prove that this is a power series root and it's unique. I'm not going to do those proofs. They are not difficult. So for the proof, we need to show that phi defined this way gives the power series root. And the way we will show this is by showing that phi of x comma phi sub m of x f of x comma phi sub m of x is 0 mod x to the n plus 1 for every m. And then one has to argue uniqueness, which is also not very difficult. And this statement as it is already has some very interesting consequences. So one consequence is the following. It's that if f has a circuit of size s and the depth of the circuit is k, then for every m, phi sub m has a circuit of size poly in s times m, poly in Sm, and the depth of the circuit is k times m. Okay, so why is this true? So I have a proof by picture. So we start from phi naught, and at this point, so this black circuit here is a circuit that computes f. So we plug in phi naught into in the place where the y variable was plugged in. We do some scaling, we do some addition. So these are all addition gates there. So I can't see them here. And you get phi 1 at this point, and then you plug this in. Plug phi 1 into the circuit in place of y, do some scaling, do some addition, you get phi 2, and so on and so forth. So for every I, we basically take a copy of the circuit of f itself and do some increase the depth by maybe an additive constant, and at the end of m levels of this, you get phi sub m. Is that good? Great. So this picture should basically prove the claim for you, assuming you believe everything we said in the previous slide. Now, this also tells us something more. So if a power series root of phi, if a power series root phi of f happens to be a polynomial of degree n, it's not a power series, it's actually a polynomial, meaning it's a power series with finitely many terms, then this statement will tell us that phi has a circuit of size poly m, depth order k. And this statement it precisely proves Kaltofen's theorem for factors of the form y minus g of x. So these are y minus g of x is a fact. If y minus g of x is a factor of f of x y, then g of x is a y root of f of x y, and g of x is a polynomial. So we can invoke this theorem with the appropriate starting point, namely g of 0, and get a circuit of depth order km and size poly in S at the end. Yeah.
So these phi's are supposed to be polynomials of degree I,
right,
or I minus 1.
Yeah.
And you don't need to go mod I minus x to
Right.
the I minus 1 here?
So there's some automatic correction that happens in the process. If I did write going mod x to the I plus 1 everywhere, then we would have to homogenize at every level, and then we won't get the circuit upper bound because there's a multiplicative increase. But we don't need to do that. It will autocorrect. So the guarantee is that phi I has the right monomials up to degree I and then some junk for phi I. Okay? Yes?
After this process, you homogenize one.
Yeah, we homogenize one.
And then.
Yeah, exactly. Yeah. Questions? Yeah.
When you have the usual version of Newton iteration, you have this property that the number of correct digits
Squares.
double
Doubles,
each.
yeah.
You don't have that with this?
So we are looking, so the version of Newton iteration we are using here is one with linear convergence. The one you're talking about is one that gives you quadratic convergence. It wasn't important here, but you could also use that and do some division elimination later. Yes?
So to start this process, it seems you need to know A.
Yes, you need to know it. Yes. Yeah. But here we are not worrying about an algorithm, we are just trying to prove bounds on the structure of circuits for the factor. So we can assume we know it. Other questions? Okay.
Maybe one comment is, I think if you want to turn it into an algorithm,
Yes.
it's only the start. Right?
It's only the start, yeah.
The rest is
Yeah. So far, it's only the start that we don't know. So we will get to it when we talk about that. Other questions? Comments? Okay. Great. So this is what I mean by constructing power series roots. We start from one of the roots of f of 0 comma y after all the pre-processing is done, and we apply this process to it to get a circuit for power series roots, truncations of power series roots. Now, at this point, at least naively, we should be able to convince ourselves that this process as it is doesn't work for constant depth circuits or formulas or AVPs. Right? It's easiest to see it for constant depth circuits. The depth, so if we are going to compute phi m, we are going to have m copies of the circuit for f put on top of one another. So there's a multiplicative increase in depth where m shows up so you have m copies, so the depth becomes at least k times that. So it doesn't work for that. If you think a little bit more, you will also see that it doesn't, as it is, work for formulas or branching programs. Okay, so what at this point, what is it that would make it work for, say, formulas or constant depth circuits or ADPs? So the nice thing about Newton iteration was that it was an iterative process, and each of the steps in the iteration was really simple to describe. This is what made us conclude that the circuit for phi m, we could get some upper bound on it immediately. So the iterative aspect of it is what made it easy to understand and analyze, and what we did so far. The thing that's a problem when we try to extend this to constant depth circuits is that the process is iterative. Right? So the depth increases iteratively. So only if we had a non-iterative version of Newton iteration, we would all be happy. Great. So there is a non-iterative version of Newton iteration which was discovered before Newton iteration in this form was discovered in the CS literature. So this is from a paper of Fustenberg from '67. There's a star here because this is some massaging of it with some work, but it will be in a form that we can use off the shelf. So here's a non-iterative description of phi sub m. This is the same phi sub m that we constructed iteratively, and Fustenberg with some work essentially gives you a closed form expression for what phi sub m looks like. Great, so let's parse this. Let's forget about the mod x to the m plus 1. So we want to compute phi sub m. The number of summands here is 2m. So there's some order m terms that we are going to sum. What does each term look like? So each term looks like you want to compute the coefficient of y to the something in the polynomial. So it's a product of two things. The first term is just the y derivative of f after some initial shifting. And the second term is y minus f of x comma y plus a raised to some power. Now it shouldn't be very hard to see that if f has a small circuit, then y minus f blah 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 raised to some power I also has a small depth circuit. Similarly, if f has a small depth circuit, then its y derivative also has a small depth circuit, and we can take them together and multiply them together, so that each of these terms, each of the polynomials inside, is computable by a small constant depth circuit. And then you have to compute the coefficient of some monomial in y in this circuit. This is something that we know how to do via very standard techniques. So each term is, if f has a small constant depth circuit, each term has a small constant depth circuit. And we are only summing a few terms. And we are doing some modding out by x to the m plus 1, which is one more level of homogenization, which is again something that we know how to do. So this expression as it is should roughly convince you that at this point, if f had a small constant depth circuit, or f had a small formula, or f had a small branching program, then phi sub m should also have a small branching program, modulo some small details. Okay, so let me wait here for a second. There are questions? Okay, yeah.
Does this mean anything? It's an expression, but does it have like analytic or something?
Yes, so the way Fustenberg came up with the expression was that there was analytic intuition to it, but then he noticed that analytic intuition translated to him writing a closed form expression, but the expression he could prove it over all fields in a more general setting. So yes, so it did mean something. It doesn't mean anything to me, but it meant something to someone. Other questions? Okay, all right. So this gives us a small constant depth circuit for phi m if f had a small constant depth circuit.
So you prove the correctness of this by just plugging it into the top line, or?
To prove the correctness of this, yeah, we can verify this step by step. Yes. Other questions? So Fustenberg's original theorem did not give this expression; it gave another expression which is far easier to prove than proving this directly. But after some massaging, this is what comes.
This is also related to the Lagrange inversion.
Right. 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 What m do we need? So think of m as being poly in the degree of the polynomials.
And
So
that will be enough.
that will be enough. Yeah, we'll have to argue that that's enough. Yeah. Great. Okay. So at this point we have a constant depth circuit that computes the power series roots of a polynomial computable by a constant depth circuit. And this is enough, for instance, to to give us a few things. For instance, if the power series root happens to be a polynomial, then this will tell us that this polynomial has a circuit of depth additively more than the depth of f. Okay, so this already proves Kaltofen's closure result for factors of the form y minus g of x. Great, so now that we have power series roots and we can talk about the complexity of some factors, let's go ahead and talk about the complexity of general factors. And the key idea here is the following. So let's say f of xy is product over I going from 1 to r, gi of xy. Each gi is a distinct irreducible factor. Now f is monic in y, with a bit of thought implies that every gi can be assumed to be monic in y without loss of generality. And let's say that phi superscript 1 up to phi superscript d are all the power series roots of f. Okay, so here's a very natural fact. Where did the power series roots of f come from? They must have come from the power series roots of gi's. So if f can be written as product over I going from 1 to d, y minus phi superscript I. And for every m in R, so for every irreducible factor, there is a subset of these power series roots such that g sub m is the product of y minus roots from that subset. Okay, this is very natural. This is something. This is almost immediate.
This GM and the GIs on the top,
They are the same.
Right?
Yeah.
Okay.
So m in R, I should have said I in R.
Uh-huh.
Okay, so in order to so this expression tells us that if we wanted to argue about the circuit complexity of G sub m, any irreducible factor of f, then it was enough to talk about the circuit complexity of the object on the right here. The problem with this expression as it is that phi sub i's are infinite objects, they are power series roots. But since G is a polynomial, it shouldn't come as a surprise that we can work with truncated versions of these power series roots. Right, so how does this let us obtain a circuit for G sub m? Well, G sub m is a polynomial, so a reasonably good approximation of the power series roots is enough to compute G sub m. So in particular, if the x degree of G sub m is capital D, then we truncate each of the phi i's at degree D, and then we do some homogenization, and you will get G sub m. And the previous theorem told us that phi sub i's, phi superscript I mod x to the D plus 1 has a circuit of constant depth and size poly in D and S. So each of the terms inside has a small constant depth circuit. We can plug it into the expression, do some standard manipulations sort of, and get a circuit for G7. So this tells us that the above expression also has a small constant depth circuit. So this completes the proof of the closure result that I mentioned. Okay, so there were 3 steps. We did some pre-processing, made f look nice. The second step was to compute the power series roots of phi of f. In fact, we computed truncations of it, and then we took those truncations and plugged them into clubbed them appropriately to get the irreducible factor.
How do you get the roots of the a's?
We are talking about. I'll come to it when we talk about the algorithm. For now, this is just a circuit complexity of it. Questions? We'll move on to the deterministic algorithm now. We have enough time to say something. Yeah.
So this is based on Newton iteration.
Right.
The other
Right.
technique is Hansel lifting.
Right.
Do you have a Fürstenberg like yourself or?
Right. No. Yeah. But it should be there. It's just,
It should be there.
Yeah. Exactly. It should be there.
So this follows over the algebraic closure of the field, right?
Right.
So
Right.
if you want
Yes.
to maintain
Yes. So that requires some more work, but I will not. We can talk offline.
what was it?
The question was, this works. We are using so these AIs, the roots that we started with, might live in the algebraic closure. So this gives a circuit over the closure. What about circuit over the base field that we started with? Other questions?
What is the context in which Fürstenberg came up with this?
So I'll have to remember, but I think it was.
So you have two power series which are algebraic.
And he wanted to show that the Hadamard product is algebraic.
Yeah, and that is a statement that is true only over
Real.
finite characteristic. It's not true over the reals.
Right.
And this particular statement was proposition
Yeah.
3.1.
somewhere inside the paper. Okay, other questions? Oh, great. So let's talk about the algorithm.
By the way, when you said something about Furstenberg's form being somewhat different than the one that you had, why did you change it?
Oh, this was easy to see that the circuit size is the conclusions we wanted. That's not too hard either, but this seemed clean. Great. So this is the deterministic algorithm for factorization of constant type circuits. I am going to focus on the question of testing irreducibility of sparse polynomials, and that's the problem I think we should have in mind as we go through this. And we'll crucially use the following theorem. So this is that we have deterministic sub-exponential time black box PIT algorithms for constant type circuits. So this is something that's going to be useful for us. And we will essentially have to use the full power of this theorem even when we are testing irreducibility of sparse polynomials. So we don't know how to do any better. Okay, let's get started. So a natural start for an algorithm would be to follow the outline of the proof of the closure result and see what parts don't work. Right, so we have a sparse polynomial as input. We want to test if it's irreducible. Remember, we had three phases in the algorithm. There was some pre-processing, there was some computing of power series roots, and then we had this issue of combining power series roots appropriately to construct irreducible factors. Most of the work here is in the third part. The first two parts will follow somewhat easily using some of the results that we know. Okay, but let's talk about them briefly. So so we are going to do deterministic pre-processing. We want to make f monic in Y, and for simplicity, let's assume f is homogeneous just for this discussion. And to make f monic in Y, we pick an A such that A is in Fn such that f of A comma 1 is non-zero. This can always be done. It takes 30 seconds to think through this. And then we are going to work. We won't work with the polynomial f itself. We'll work with the polynomial f of x plus ay comma y. So we'll shift all the variable xi by ai. We'll move xi to xi plus aiy. Okay. Great. So how do you find some an A such that f of a comma 1 is non-zero? Well, this is where we need PIT for the class of circuits that f lives in. For sparse polynomials, we can do this in deterministic polynomial time.
This is black box PIT?
Here, this is black box. Okay, and we can find this shift using PIT for sparse polynomials. So this will make, at the end of this very simple exercise, we'll get an f that is monic in Y. Great. So what was the second part of it? This was the question of testing square freeness or making f square free. But notice that we are here in the problem is to test irreducibility. So if f is not square free, it's not irreducible. So it's enough to test the square freeness of it. If we can test it in deterministic sub-exponential time, we are good. So how do we test the square freeness of f? So we are going to f is square free if and only if f of x comma y and its y derivative do not have a non-trivial GCD. And we are viewing both these polynomials as univariates in Y. And how do we test if two univariates don't have a non-trivial GCD? We construct the resultant and we want to check if the resultant is non-zero. How do we check the resultant is non-zero? Well, Avi and Robert showed that the resultant is a constant depth circuit in this setting. So if f is computable by a small constant depth circuit, then the resultant of f and its y derivative, which is a discriminant of f with respect to y, is a small constant depth circuit. And so it computes a polynomial in x, and we want to test if it's non-zero. But we know how to do PIT for constant depth circuits and deterministic sub-exponential time. So we can do this deterministically in sub-exponential time. Okay, that was a little quick, but again, it's an off-the-shelf use of things we know. So there's a third part of it, which was to ensure the square freeness of f of 0 comma y, and this is with a moment's thought you'll see that this is also just a PIT instance. So we'll find a b such that the resultant of f and its y derivative doesn't vanish when x is set to b. And this is again because of the discussion in the previous slide. This is a small constant depth circuit, so we can do this in deterministic sub-exponential time. Right, so we are going to work with f of x plus b. So we first shifted x by we made xi to be xi plus ai times y. And then we shifted it further by vi. So we are in the setting. Going forward, we are going to assume that f is monic and has all the nice preprocessing properties that we wanted. There's one little bit of little more work that we have to do here, which is to okay. So we want to view f as a bivariate right now. So we had two views of f. F was a multivariate polynomial, and then we viewed f as a univariate in y, where the coefficients were in C adjoint x. But now we want to view f as a bivariate. The reasons for this will be clear later, but for now, let me tell you how to do this. What we are going to do is we'll take a new formal variable t, and we'll replace xi by xi times t in the polynomial. Okay, and so this new polynomial has three sets of variables. There are x variables, t variables, and y variables. X variables, t and y, and we are going to view this as a bivariate in t and y. And the x variables are all going to be pushed into the underlying field. Okay. So here's the fact. I'm not going to prove it. It's not difficult to prove. Which shows that factoring this polynomial, capital F, in this ring, it suffices for factoring the original polynomial we started out with. So we are going to view capital F as a bivariate in t and y with coefficients in this field k, and we are going to factor it. And somehow that, in a very black box way, translates to factorization of f of x. This is one of the many things that's called Gauss's lemma. This is an easy application of that. So one thing to observe here is that since we ensured that little f is monic in y, capital F continues to be monic in y. This process of setting xi, making xi to be t times xi does not affect that. If little f was square free, capital F continues to be square free. And if little f was square free when x was set to 0, capital F continues to be square free when t is set to 0. Okay? Great. So at this point we are done with the pre-processing. Now we are in the second step where we want to compute power series roots. And for simplicity, I'll assume that when we set t to 0, the univariate polynomial in y that we get. So remember, xi came with xi was substituted by xi times t. So when you set t to 0, all the xi variables also vanish. So what you get is a univariate in y. Let's assume for the moment that they have all rational roots. So we can actually compute these rational roots efficiently and deterministically by the LLL algorithm. So let's do that. Let's compute A1 up to AD. And then we can start from each of these AIs and lift them to a power series root modulo some power of t. And as Peter pointed out, once you get a starting point for Newton iteration, the lifting process itself is completely deterministic. So there's no randomness used in this process. So we got our hands on AIs, and from here we'll apply the lifting process to get our hands on truncations of PI up to sufficiently high accuracy. Great, and we have the guarantee that each of these truncations is a small constant depth circuit. If the original polynomial we started out with, we actually started with a sparse polynomial. In that case, you get a constant depth circuit for each of these.
So is it now are we assuming we have rational polynomials, for instance? Or?
Yeah. So we are assuming this one. Yeah. So let me briefly say what happens if you don't have it. So if you don't have it, you still apply LLM, factor f of 0, 0, y into a product of irreducibles. Take one of the factors and construct an extension of rationals which contains roots of this irreducible factor and work with that. And there is a way of doing this.
But here you don't need the lifting, right? You could just use your formula. If you
Right, exactly. So you could, yeah. Oh, by lifting I mean use the formula.
Oh, okay, okay.
Yeah.
Good.
Okay. Other questions? Alright, so what we have done so far is we did some deterministic pre-processing using PIT for constant depth circuits. We got into this, we made this change of point of view from working with f of xy, little f of xy to capital of f of x comma t comma y. And we were viewing capital F of x comma t comma y as a bivariate in t and y. We set the variable t to 0, we got a univariate in y. We computed its roots using LLM. We assumed that all the roots are rational, so we can actually do this. We picked these starting points and found ourselves good enough truncations of the power series roots using the formula in the previous discussion. Prahlad, question?
So why is famous we do polynomials in X and not
Great.
rational functions?
So
Because isn't the derivative
no,
have
it's
been
not. Remember, in the derivative we set t to 0, so all the x variables vanish.
in the derivative? Okay.
Yeah. So it is. Yeah. So these are actually polynomials in X. Other questions? All right. So all of this can be done deterministically in polynomial time, and all we need to do now is to somehow use these these high enough accuracy truncations of the power series roots to somehow test irreducibility. But notice that everything we have done so far, we could have done with any square-free polynomial. We could have started with an irreducible polynomial that is square-free and by definition, and we could have done everything we have done so far for that. So we haven't done anything to distinguish irreducible polynomials from reducible ones so far. So let's do that now. So how do we certify irreducibility using these power series roots? And that's the following lemma. So f is irreducible if and only if for every non-empty proper subset S of the power series roots, the polynomial q sub S doesn't divide capital F. What's polynomial q sub F? It's this. Okay, so we have all the power series roots. F is irreducible if and only if for every proper subset of these power series roots, we construct this polynomial q sub S. And we check whether q sub S divides the polynomial F. And the form of q sub S should remind you of the form of g sub m that you were writing earlier. Okay, great. Furthermore, this non-divisibility condition is equivalent to testing if a constant depth circuit C sub S that takes the coefficients of F as inputs is non-zero. So for every subset S, if the circuit C sub S that comes out of this lemma happens to be not identically 0, then F is irreducible, and it's an if and only if condition. So given the power series roots, in order to test if F is irreducible, all we need to do is to construct this circuit C sub S for every proper subset S of the power series roots and check if it's non-zero. Okay, but there are many, and since C sub S is a constant depth circuit, given any such circuit, we can check if it's non-zero or not in sub-exponential time, deterministically. But the problem here is that there are too many subsets to worry about. Okay. So F is irreducible if and only if all of these circuits are non-zero, and so I'm about to run out of time. Yeah, so I mean at this point we essentially do this using the PID for constant depth circuit. So what we show is that so PID for constant depth circuit gives us a variable reduction map that reduces n variables to n to the epsilon variables while retaining the non-zeroness of constant depth circuits of small size. We show that this map also preserves irreducibility. So the way we argue that is by essentially arguing that it preserves the irreducibility of each of these small circuits C sub S. And then so there's some superficial work to be done on top to make sure that this the variable reduction in X doesn't affect everything that we did before while reaching up to this point. Okay, but in a nutshell, we have characterized irreducibility by non-zeroness of an exponentially large subset of constant depth circuits, and we use PID for constant depth circuits to do this somehow at this point. Okay, so let me not say more, but this gives an algorithm that runs in time d to the n to the epsilon. Great. Okay, so let me end with some open problems. So the connection between PID and deterministic factorization here was very, very black box. We use the fact that we have a black box algorithm, including in the step that we just talked about, if you think about it. It'd be nice to have a white box, a connection from white box PID also. For general circuits, such a connection is there in this work of Amir with Swastik and Shubhangi. Computing p roots, I think, is a very nice question, very basic, should have a nice answer maybe. It would be nice to understand this better. And factor conjecture, of course, is also a very nice question to think about. Okay, so these are the two theorems, but maybe the thing to take away is the theorem of Shanthanu Rai.
for this beautiful survey. And at the beginning you had this assumption of characteristic zero.
Yeah.
Now I'm wondering, I'm sure there are open problems.
Right.
I mean, if you are in positive characteristics, I mean, if you do Newton integration, like this division.
So in positive
just
characteristic,
I guess there also the divide things. So I wonder what.
so the issue is, one of the issues is that we don't know how to factor univariate polynomials in deterministic polynomial time over positive characteristic. So this univariate factorization step where we looked at f of 0 comma y and we said compute the roots of it is not something.
Let's say the structural result with that.
The structural result will hold up to this p power problem that will also.
This is the only thing that is.
This is the only thing that affects us. Yeah. Yeah, the algorithm has that issue about deterministic univariate factorization,
But this is only if the p is large.
right. That's it. Yeah.
Okay, thank you.
Other questions?
So do we
No explicit polynomials where we believe the blow up in the factors are as large as possible?
So I think we don't have too many. We have essentially one family of examples that I know of. Every other example that I know of sort of is very closely related to it, but we don't know. So that we don't have a good understanding of that question. We don't know examples. We don't have upper bounds. We don't have good lower bounds.
So there are no